Today we're going to talk about the traveling salesperson problem. This is your next assignment. I'm going to try to give you a little bit of context on why this is an exciting problem, why it's interesting to look at it, and how it's important for computer science. Then we're going to talk about what the assignment is for those of you who haven't yet read it. And then I'll start giving you a couple of tips and tricks that may help you do this assignment. So first to start, we should all be on the same page as to what the problem is. So the traveling salesperson problem, you are given a set of n cities. And so the point is that you imagine a person that wants to drive to all of these cities, one after the other, using the least amount of gas or mileage. So that's why it's called the traveling salesperson problem. So from the set of n cities, you want to return a circuit. You start and you end at the same city and you go through all of them. In this assignment, we call this a tour. So here's an example of one possible circuit, right? So we go to all of the cities and we cross. But of course, that's not the only possibility. There's another one that's the following one here. And another one, and another one. So the first question we should ask ourselves when we're playing around with this problem is, how many possibilities are there? So given a set of n cities, how many of these possible tours could I possibly generate? Well, let's number the cities from 1 to n. So here from 1 to 5. And so now we know that the order in which we visit cities is a permutation. We know that there are n factorial such permutations of n numbers. And the only thing here is we must account from the fact that with permutations, you could take things in one direction or in another direction, but here we just want to normalize so that they're all in the same direction. And the second thing is that with permutations, you could start at any one city, which happens to make the same tour. So to account for that, we're going to divide by the number of starting points, so that all of our tours start in the starting point 1. So when we add those corrections, we have n factorial ordering, divided by the two possible directions in which you can circle around the tour, divided by the number of cities. So the overall number of possible tours is half of n minus 1 factorial. Okay, so let's apply this to n equals 5. For n equals 5, half of n minus 1 factorial is half of 4 factorial, is 4 factorial divided by 2, so that's 12. More generally, half of n minus 1 factorial can be approximated by n to the n exponential. So what this really means, this is a lot of math. To be precise, you don't really need to know how to wield it, but it's just to give you a sense that there are a lot of possibilities. And to make our problem more complicated, we're not just interested in any one of these tours. We're interested in the best one, the one that's going to minimize gas mileage. So of these tours, could you tell which one is the best one? Could you just take a couple seconds, look at all 12 of these tours and sort of think which one is the best one? Right, so the best one is the one that's the tautest around the city, and so it's this one. Okay, but the idea is that this is sort of like a needle in a haystack. There's only one of them that's optimal, but there's a whole bunch of them that are possible. So the difficulty of this problem is in this ratio between the one optimal solution and the many non-optimal ones. So of course you could tell yourself, well, 12 isn't that bad a number, and it was easy enough to find. But of course, we're never going to work with these types of toy problems. In real life, you'll be faced with something like this. So here, this is a TSP of all of the National Register of Historical Places in the United States. So there's 49,000, and that required a lot of computational power to compute. So that's something you can find on the web. Somebody spent a lot of time and big computer rigs to compute this tour exactly, and this is the optimal tour. Okay, so to be a little bit more precise, what we're talking about here are what we call combinatorial optimization problems. As I just said, the only way to find the optimum for traveling salesperson problem is to look at all of the possibilities until you've found the best one, or the best ones if there are multiple with the same cost. So as you can see here, the growth of the number of possible tours given the number of city really grows really fast. So for n equals 5, the example that we just did together, we had 12 possible tours. For n equals 6, you have 60 possible tours. For n equals 8, you have 2,000, and then as soon as you go above, then things just become intractable. As soon as you have 18 cities, you have up to 100 trillion possible tours. So of course, even with a very fast computer, you can't possibly analyze and look at each of these 100 trillion possible tours, especially if you only have 18 cities. That doesn't make any sense. So generally, all of these combinatorial optimization problems are the ones for which, if you don't make any heuristics, you're going to end up with this n factorial performance. So n factorial, remember in the precept where we had performance, you had n factorial. Well, this encompasses all of these combinatorial optimization problems. We don't know how to make a good guess, so we have to look at all possibilities and pick the right one. So in practice, of course, we're not going to look at 100 trillion possibilities. That's just a waste of our time. So what we're going to do is we're going to use heuristics, which help guide and eliminate the obviously wrong solutions so that we don't waste a lot of time on those. And more generally, TSP belongs to a broader class of universally difficult problems that, similarly like this, do not have straightforward solutions. So those problems are called NP hard, and they're going to be a point of the future lectures on theory of computation. Okay, are there any questions on this so far? Okay. So for the TSP problem now, you might ask, well, what are the heuristics that are going to help us do this more efficiently? Well, the two heuristics that we have are the nearest neighbor heuristic and the smallest increase heuristic. So let's take a look at both of them on this small example with 3 points. So you have 3 points here that form a triangle, and they've been inserted in the order that they're numbered. So 1, 2, and 3. And this order of insertion you're going to see is important. So in the nearest neighbor heuristic, we're trying to insert this blue point. And so to insert this blue point, the way that we're going to insert it is we're going to measure the distance of the blue point to all of the points in the existing tour. Okay? And we're going to insert the blue point after the point to which it's the closest. Okay? So here, as you can see on this diagram, the blue point is closest from point 2. So that's in the middle diagram. So therefore, in our tour with 4 points, we're going to add the blue point connected between 2 and 3. So that doesn't make a whole lot of sense. You have this sort of like crossing. You can tell that it would be better if you didn't have that crossing, but that's what this nearest neighbor heuristic will say. And that's why we'll see that we can improve on it. Okay, so now the nearest neighbor, the smallest increase heuristic is slightly different. So I'm sorry, I didn't realize that the blue wouldn't be seen, but here smallest increase says select a point that minimizes the increase of the tour. So here, in all of these examples here, what the algorithm does is it measures the distance between point 1 and point 2, and then it compares that to the distance between point 1, the blue point, and point 2 if it were inserted between point 1 and point 2. Then it does the same thing, and it measures the increase of inserting the blue point between 2 and 3. And then it does it again, measure the increase of adding the blue point between 1 and 3. So in these examples, the smallest increase is when the blue point is added between 1 and 2. So that's the insertion that this heuristic is going to choose, and it's going to lead in this result. Okay, so what you can see already with this example is that depending on the heuristic, the final tour that we have might be different. Okay, and so in this case, the final tour with smallest increase is better. Okay? So now we might talk about some of the applications of TSP. So as the name suggests, it's very useful if you're planning to sell encyclopedias, but there's a lot of other applications. So think about school bus routing, for instance. A lot of these applications were in public policy. More recently, since we're all online shopping, it's becoming really important for UPS, FedEx, USPS, Amazon, all of these companies that are operating last mile vehicles to optimize their delivery. But of course, the TSP problem is also just a model with which to tackle other problems that have nothing to do with logistics. So it's not surprising to find applications in genomics, in medicine, or in circuit board printing. So like here, this example here is an example of a robot that prints circuits and that drills holes in circuits. Here in front are the different drill sizes, and so the robot is going to pick a different drill to do the different holes. And since on a given board there are a lot of different holes of different sizes, the best way to avoid mini switches is for this robot to do a TSP with each drill size and to do the best tour for each drill size, so it only has to change a very small number of times. So there are very many applications, and you'll see that the TSP model is a very flexible one, a very powerful one. You can replace the cities by genomes. You can replace the distance by healthiness or something like that. It doesn't have to be distances. If you want to see more of these applications, I've put a link down below, bit.ly/TSP applications PDF. So that's the problem, and now we're going to talk more about the specifics of our assignment here in 126. So your job is to implement the Tor API. The Tor API is the data structure that's going to take these points and create a tour, a circuit of them. So you're given a sequence of points. So here I've lied a little bit and I said that it's a point array. In the assignment, they're given one after the other. You never see them all in an array. And so your job is to output a tour. So with the heuristic that you are asked to do. So it could be this tour, it could be another tour. You're going to create the data structure that stores these tours and that allows us to use one or the other of the heuristics when we're inserting these points. So the API of the tour is as follows. There are two constructors. The first constructor creates an empty tour. The second one creates a tour with 4 points. So that's going to be useful for testing properties. And then you have two sets of methods. Some that simply look at what you currently have. So that's length, size, the number of points in the tour, length, the contour of the current tour. Draw is going to output a drawing of the tour. And then you have methods like insert nearest and insert smallest that modify the tour so that they're a little bit harder. And then you, of course, have your main method to test all of the methods that you're implementing. So if you take a step back, the diagram of the models and the classes in this assignment looks sort of like this. So you have a big Tor instance, that's the class that you implement. And inside the class that you implement, you're going to create a circular list. So you're probably going to have an instance variable called head or first or start. And you're probably going to have an internal class of nodes, like the circular quote that we've seen in Precept. And each of these instances of node is going to store two things: a pointer to the next element and a pointer to the point that this node contains. So you see that your actual project is going to manipulate node instances, point instances inside of your Tor class. So the goals of this assignment, the broad goals, are you have to deliver this Tor.java file and a README with an analysis. You are provided a lot of things. You're provided the point.java class. The node class is given to you. We've also shown in precept exactly what you need to do. And you're provided with several test clients to often test what you're doing, and also a lot of data to easily try it on non-trivial examples. And that will enable you to check whether your implementation is correct. But if we take a step back and we look at what the broader goals of this assignment are, well, they are, the questions that we want to find out is, can you use a data type that is provided to you? So how do you use the point object? Do you make a good use of it, or are you having a hard time figuring out the barrier of abstraction? So I'll talk a little bit about that in a bit. Second question, can you use a private node type? So the thing that we've introduced in this precept with the circular list is this idea that you have a class, and inside of it you have a nested class. So I think we've already seen this notion a couple times, but here we really want you to play around with it. So are you able to define your private node inner class, and are you able to use it correctly inside of your linked list? Can you traverse a list? So that's the point of tour.size and tour.length. Just having an existing list and going from the beginning to the end. And what about when there are different base cases? So tour.toString can be a little bit different depending on how you implement it. And finally, can you modify a circular list? So that's the hardest part. So the reason why it's the hardest part, notice first of all, is that's why in the API we have tour that takes 4 points. Why? Because it's a lot easier to create a simple list with 4 points in that constructor than to get the insertion methods right. So the idea is, by implementing that constructor, you can then test size, length, toString, and draw without having to implement the insertion code. Okay? And those are things that we'll talk about a little bit more. So now let's look at one of the test clients that we provide you. So it's very useful. TSPVisualizer uses your client but provides a graphical interface. So in it, you're allowed to pick points one by one and to see the outline that both heuristics would provide. And of course, if your implementation is incorrect, the result of this visualization is going to be incorrect because it uses your implementation. So here's an example of TSPVisualizer. When you open it, it provides you instructions on what keyboard commands you can use. This test client is simply going to call your draw method, so it has to be implemented. And to color it differently, it will make a call to standard draw.setPenColor.standardDraw.red or .blue, depending on the heuristic. So the client can take a set of starting points. If you don't want to re-click the same 4 or 5 points every time, you can just put them in a text file and read them into the program as a starting base. So here I'm going to give you an example of just some points that we've done with my implementation of TSP, just to show you how this is supposed to behave dynamically. So here I click, I add a point, I add another point. And so both heuristics are the same. Another point, another point, another point. So up until now, I'm only displaying the nearest heuristic, the one that's in red. But as you can see below, it gives the tour of both the nearest heuristic and the smallest heuristic. And here you can see that they're both the same size. So initially, nearest neighbor heuristic and smallest increased heuristic appears similar. And now I'm going to try to find an insertion that's going to maybe make the nearest neighbor less sufficient. So here, if I click in this place, well, what's the increase that I would expect to make, the one that's efficient? It's just to raise the tour edge that I'm under below. But remember, because of the way that nearest neighbor inserts point, I'm going to have a crossing here. And that's obviously not what we really want. So here at that point, you'll see the nearest is 1,034, and the smallest is 947. So here, this is where the nearest neighbor heuristic got trapped, where the smallest heuristic knew better. So it depends on the order in which the points are inserted, and that's very important, right? So here in the terminal, it outputs all of the points. That's the output that I could provide as a text file if I wanted to reload these points. And now I'm going to show you the blue heuristic. As you can see here, it didn't get fooled. It did exactly what we expected it to do. Okay, and so here, same thing. When I'm clicking on this point, I'm only going to extend the smallest increase by a little bit, but look at that nearest that made a jump of another 70 because, of course, it's crossed as well. Okay, so one question that you might ask now, once that you've implemented these heuristics, an interesting question is, well, what's the worst case scenario for one of these heuristics? So I was playing around, and so one of the things that I saw is if I create a very, very narrow triangle like this, well, if I point on the other side of the triangle, I'm able to make the nearest neighbor do a big jump, and I'm able to make it do another big jump up here, and then down here. So here, in just 3 clicks, I've been able to make the nearest neighbor really less good than the smallest insertion. So if ever you get curious or something, one question that I would ask you is, can you find a systematically bad way of building sequences of points for our nearest neighbor heuristic? And could you write a program to generate a really bad sequence, one that maybe has a difference of 10,000 between the nearest neighbor and the smallest increase? So that's the kind of interesting problem that you could think of. So now let's get to tips and tricks on this assignment. So I was telling you that one of the important parts is, can you use a data type that you're provided? So take a look at this points API. So what is one thing that's particularly noteworthy about this point API, at least from my point of view? So it's a point API. It's a data type that stores coordinates in a grid, so x, y, points. And a thing that's very surprising to me, but is actually not an accident, is that there's no way for you to get what those x and y coordinates are once the point has been created. So none of those methods allow you to recuperate x or y as a numerical value. So that's, of course, going to impact how you use the point class. So for instance, so another challenge for those of you who are bored by this class meeting is, how could you use just these methods, so distance to, draw to, and toString, how with just these methods could you recover the actual x and y numerical values? So this was just a thing I was playing around with, and I found a solution that is math-based and a solution that's text-based. But these are both pretty challenging, and I'll show you the code at the end if any of you want to think of it. So in tour.length, to measure the perimeter of the tour, what are you going to use? Well, since you don't have access to the points yourself, you're going to use point.distance2. And to a certain sense, it's an advantage for you because you don't need to remake the geometric computation that, well, I don't know about you, but I'm glad that I didn't have to redo it in this assignment. So same thing for tour.toString. So tour.toString asks you to provide an output of all of the points contained in the tour in the order in which they're linked. Well, so obviously, you won't be able to print the coordinates x and y, but what you will be able to do is directly use point.toString. Okay, and so final example, you have to implement tour.draw that draws a tour, the surrounding of the tour on standard draw. But obviously, if you don't have the coordinates, then you are going to have to use the method point.drawTo that draws a segment between the actual point and another point that you provide as a parameter. Okay? So now the other point is, in this assignment, you get to be introduced to circular linked lists. So this is sort of a mind-numbing concept, this idea that you have a list that loops to itself, but it's one that we've introduced in Circular Quote. So if you think about it, the circular list is something just like this, where you have an instance variable head or start or first that links to the first element in the list. And then each element links to the next one in the list until you get to the last one that links back to the first one. The reason why circular lists are useful is they allow us to treat every case like it's the same. We don't have to distinguish between the beginning of the list and the end of the list. We don't have to keep checking whether the next pointer is null. We can just assume that it's not null and follow the link until we've gotten to the place that we want. So circular linked lists are used to make code a little bit simpler. We'll show exactly how a little bit later. But they can be tricky because you have to make sure that when you insert a link, you break the list and you reconnect it. So here, as I was saying, in the beginning, when you want to test your operations like length and size, it's useful to be able to create a TOR list that doesn't require you to make point insertions. So that's why you have the TOR constructor with 4 elements. So the TOR constructor with 4 elements just asks you to do the example that we've done in Precept with inserting 1, 2, 6 into a list. So that example was fully covered. It's documented in the slides on the Precept page, and it provides you exactly what you need to put in that constructor, except that you have only 3 elements in our example instead of 4. Well, what I've done to make testing even easier is I've gone ahead and say, well, I don't just want to specify. So here in this example, you have to give the coordinates of the points every time. Well, I know that giving a bunch of coordinates is going to I'm not going to do it because I'm lazy. And so what this probably means is I'm not going to test a whole lot of things if I have to enter these coordinates. The way I get around this is I use a lot of helper functions to enable me to be curious about tests, because I know I'm very curious and that I would like to test a lot of things, and it just really boils down to time and how convenient it is. So with helper functions, I can make testing and exploration a little bit easier and more straightforward. So how do I do this here? Well, in this example, I created a helper function, create square tour, that just allowed me to create a bunch of squares of different sizes, differently shifted around the setting. So I created this method, create square tour, that takes a parameter alpha, that's going to be the size of the square, and a parameter beta, that's going to be how shifted it is to the edge. So inside of my code, I just have the constructor with 4 points, and as you can see, I use beta and alpha to compute the points that I want to have here. So I've given you 2 examples here. Draw square 0.85, so that's a big square with just 0.1 of margin. And then a smaller square, draw 0.4.0.5, that's has this 0.4 margin and is smaller in 1/2 of the plane. The reason I'm doing all of these squares is because, yeah, if you test your methods on 1 square, then probably it will work on a lot of squares, but you never really know. So it's nice to do a lot of different tests in a lot of different situations to make sure that we're not accidentally benefiting from some coincidence that will pan out when we're giving our code to a client. So then once I've created this square tour, how do I use it to test my methods, right? Because even though we tell you should at least call your methods once in main, that's not really testing anything. That's just making sure that you don't have a compilation error. But to test the methods, I want it to be automated whether it's good or not. So here, I'm going to create a method, test1, which will return true if all of the tests that it's done are correct and false otherwise. And that will help me build functions that collect more and more of these tests and return true or false, just like we design your test run script output, with pass or fail and numbers of tests at the end. That's the most efficient way for you when you rerun a whole bunch of tests to see very quickly whether some have failed and how many have failed and which ones have failed. So here in this case, how do I test things? Well, I create a whole family of tests that just take an alpha parameter. I give this to my creator, so I create another version that doesn't have a beta parameter. And then I test whether the size returns what I expect it to. So since I've inserted 4 points, size should always be 4, never something else. And then the length test depends on the parameters that I've given. So since it's a square, it's going to be 4 times the side of the square. And since I can't do an equal comparisons with floats, I just compare the length with what I think it should be, and I make sure that it's smaller than some sort of epsilon threshold. For those of you who've been following your comments on code posts, of course, one thing I did here that's not so good is that I hard-coded 0.001. I should have made that a constant and called it epsilon, but I didn't have enough room here. So here below, you can see how I finally call this test1 function. So this is the code I would have in main. As you can see, again, since I created create square tour, and test1 to be able to make a lot of tests, I'm not just going to be happy calling it once. I'm going to call it a whole bunch of time. And since I'm too lazy to come up with different values for alpha, and since I don't want to think of, increasing values, what I do is I simply draw a random value for alpha. If ever this test fails for one value, aha, I will have found a bug, and then I can investigate. But I expect that most of the time this is going to not do anything at all, and that's okay. But it means that I've done my due diligence. Okay? So now we can, so helper functions are very good for testing. As I just said, any method that makes it easier, that makes it more convenient for you to test is a good helper method. Because what it really is about is empowering your natural curiosity, of which I'm sure all of you or most of you have. And if you don't have it in CS, you probably have it somewhere else, of course. So I've shown you how to use helper functions for testing. I'd like to show you how I've used helper functions to make insertion a little bit more manageable. So why do we talk about helper functions? Because in programming and in computer science in general, modularity is often very desirable. It's an incredibly desirable property. It's something that comes from the origins of computer science as a math field. So in math we like clear, very abstract concepts that all work together, and a lot of that ethos has been brought to computer science. So helper functions can be useful in many situations because it helps you focus on what a specific function is supposed to do, and it helps you contain all of the problems that might arise to that specific function. So here, one particular way I've used a helper function is to avoid duplicating the same logic that is a little bit tricky in a bunch of different places. So in both insert nearest and insert smallest, I have to do this operation where once I found the point that is the good point, the one where I want to insert after, then I have to create a new node, put the point in it, and then attach it between this point and the one after. So that's an operation I have to do both for smallest and for the nearest neighbor insertion. So since I don't want to copy this code in 2 places, a good way of tackling this is to create a helper method, which I've called insert point after. So this helper method takes a cursor, so the point after which you want to insert, and a point, and it's going to take care of what I've just said for us. And I'm going to be able to call this method both in insert nearest and in insert smallest. So on the disadvantage side, if this method doesn't work, it's going to mess up both my implementations. And I might not realize that because I'm looking at the code of the insertion and not necessarily at the code of the helper methods. But on the flip side, it's much likelier that we're going to get this right And then once we get it right, we're not going to have to worry about it in the heuristics. And in fact, what's nice is that we can test this method with our square tour, right? We can add just 1 point. So we can test it outside of the insertion heuristics. And so that makes it easier how we can break down our assignments into small steps that have manageable goals that we can test. So another way that helper functions are going to help me out is to make my code clearer to understand, even if I don't have the same thing happening several times. So an example of this is in the smallest increase insertion. So in the smallest increase insertion, remember a bunch of slides back, what we have to do is we measure between the points 1 and 2, and then we measure between point 1 and the inserted point and point 2 and the inserted point. So we look at this sort of triangle inequality, and we try to see whether between which points the insertion results in the smallest increase. So for every point, you have to compute that smallest increase. So given a point that already exists in the tour and the point that you want to insert, you want to compute what the increase would be of inserting it there. And you want to do that for all of the points before you decide where you want to insert your point. So that operation, it's convenient to do it in a helper method because it's going to make your code for the insertion of smallest increase a lot less complicated. Instead of having this whole computation and calculation inside of your loop, you have it abstracted as a nice method that has a very intelligible name. And so when you reread your code or try to convince yourself that it's doing what it's supposed to, or when we're grading your code, everything is going to be a lot easier to understand. And easier to understand always is better code in programming. Okay? So now I was telling you about what the whole point of the circular list is. So the whole point of the circular list is to try to minimize the number or the difficulty of the edge cases or base cases or corner cases. Those are 3 words for the same thing. So let's go back to our circular list. So one important part of this assignment is for each method correctly identifying the smallest possible number of edge case for your list operations. And if you're able to correctly identify this number of edge cases, it will drastically reduce your code complexity. So what do I mean by that? Well, this is a list that has a bunch of elements, but you're going to have edge cases. What are they? Is it just when there are 0 elements? Is that an edge case? Or is 1 element also an edge case? So that depends on the data structure that you're using, and that also depends on the method that you're writing. So some methods are going to vary. But the idea is what you want is the more general case and implement it and then be done. Every exception that you have to take over is another if statement that you have to handle, maintain, debug. So you want to make sure that you're using the smallest number of if statements. So what I was saying earlier is that the circular loop allows you to often pretend as though you only have 2 cases, either 0 nodes or many nodes. And unlike when you have normal lists, you don't have to treat the case with 1 node separately. And so to do this, you are going to have to use the do-while construct, which we've never really talked about, but that was introduced in the circular quote example. So the way the pattern follows is like this. You simply need to test once if your head or start or first is null, so that will tell you whether the list is empty. And if it's not empty, then you can just use the do-while construct to traverse it without ever having to check if next is null. The only thing you have to do is to make sure that you haven't looped back to the beginning. Okay, so if this isn't something that's familiar to you, I strongly encourage you to look at the circular quote solution that's on the Precepts webpage. Okay, so we're almost done with these tips. So the last thing I wanted to cover with you is just the pseudocode of the TSP approximation. So here we're going to do for every endpoint, we're going to repeat this inner loop. And this inner loop is basically the code that's going to be in your insertion methods. So this is explaining how you decide how to insert a point and how you insert it. So the way you do it is like this. Imagine you have to insert a point P on a tour that you've already calculated. So the way to do this is like this. You initialize two variables, best value so far and best candidate so far. So best value is going to be the increase or the distance, and best candidate so far is going to be the point. And then for each point of the tour that's already on the tour, what you're going to do is you're going to compute the value, so the distance or the increase of the point you want to insert with that point that you're considering, and compare it to all of the best ones that you've calculated so far. If it's smaller than the best one you found so far, then you're going to update this best value, and you're going to change the best candidate that you're considering. And you're going to continue until you've gone through all of the points. At the end of this loop, best value so far contains the smallest increase or the smallest distance, and best candidate so far contains the point that you should be considering. So then you can use the helper method that you've implemented on my wise advice to insert the point after the best candidate so far that you've found. Okay? So I'm going to post these slides, and I'm going to try to post a recording of this, so you'll be able to look at this scheme at any point. But now I just wanted to talk about a few applications and a few extensions to this. So you are provided the opportunity to submit extra credit, and I've already seen some of you give this a chance because there's a lot of things that you could do. The sky's really the limit. And I wanted to give you a real-life example of an optimization. So for instance, a couple years ago, an article came out, a press release from UPS that was really proud to explain that they use some TSP algorithm in their systems to make deliveries. And it really saves them a lot of money. So to give you an example, eliminating just 1 mile per driver per day over 1 year can save them up to $50 million. And so one of the interesting optimizations that they've done to save a lot of money is to realize that they should prioritize right turns. Because as you can see in this illustration here, whenever you make a right turn, you can make it without waiting for what's happening with the rest of the traffic in an intersection, often in the US. But if you have to make a left turn, then you have to wait to make sure that the path is clear. And during that time, your vehicle is idling and is spending gas. Well, that's gas that UPS would much rather not have to spend. Another example of a very popular optimization. So this is the most popular optimization used for TSP, and it's so popular that nobody refers to it anymore. So the Lin-Kernighan Heuristic by Shen Lin and Brian Kernighan, who of course, as you know, is teaching at Princeton, was basically a generalization of these two optimizations. So the idea is this. You find 4 points or 2 edges in your tour that are crossing, and you decide to erase them and to replace them by edges that aren't crossing. So that's the 2-opt generalization. The 3-opt generalization is similar. So you identify a bunch of edges that are crossing or that you think that you could get rid of and efficiently do so. You eliminate them and you replace them with better edges over here. So the Lin-Kernighan heuristic allows the TSP algorithm to do that for K. So it starts with any given tour, one maybe that you've computed with nearest neighbor, and then it repeatedly looks at how to select K points to improve the tour a little bit. And it repeats that until it has an optimum or near optimum tour. So in practice, every solver uses this algorithm or an ancestor of this algorithm to get as close as possible to the optimum. So here's the challenge for the board. This is the solution to the 2 questions that I've asked. And since there's not only coding, I have also wanted to talk a little bit about the analysis. So the analysis is something that we often don't give a lot of details about, so I just wanted to give you a couple tricks. Here is all of my output for the running times of both nearest and smallest. And so I've done it until the experiment lasted longer than 60 seconds. So the way that you then compute performance is by using the doubling method. So we assume that the performance is polynomial. Again, we assume that it's polynomial. We use the doubling method, and so we can solve B and A. So that's fairly straightforward, and I'm not going to bore you too long about it. But what I do want to tell you is that creating your data set is an important part of this. So the way I do it is, again, I use helper methods to allow me to not make this testing part tedious. So I've borrowed this method from TSP Timer to create a random point set of size n. And then I've used this random point set to make a whole lot of measures, both with nearest and with smallest. But it's not enough to make measures. I should be able to compute them and to manipulate them very well. So one of the tips that I suggest for you is to create a CSV file. For every row, every experiment, I create a list of comma-separated values. So for every n, I create n, a line with n, the length for nearest, the time for nearest, the length for smallest, and the time for smallest. So then I generate the file in my terminal up here, and I copy-paste it in Google Sheets. Okay, and once you copy-paste in the top corner of Google Sheets, you'll see this little icon here, which asks you to split the text into columns. So if you go ahead and split the text into columns, you're going to have your data as a nice spreadsheet. So then the only thing that you need to do is create a new column, double nearest, and put the formula for the doubling method there. And then you can drag it and create the doubling method for all of your points. So you see how this makes testing just a 5-minute operation and nothing very complicated, because you can see here that it's easy to see that my runtime is converging to n to the 2. And then a final trick is, if you're not convinced by the convergence of your estimates, the best way to get more precise ones is to average. So here, if you're not happy with the way that this converges to 2, then the best way is to say I'm going to average it over 10 experiments. So here I just generate 10 random point sets, and I average the time for each of them given on the different methods. And so finally, a question for the curious. Once you are in your spreadsheet, if you want to discover something pretty cool, then I invite you to compute the ratio of length nearest and length smallest, and you'll be surprised to see what appears, I think. Have fun.